So as we start the gases chapter, we're going to be looking at the details of gases in terms of their behaviors as well as their interrelationships with pressure and volume and things of that sort. So if we take a peek at the physical characteristics of gases, many of these you guys probably understand intuitively. If not, you've studied them in general chemistry or regular chemistry. So basically, if we take a gas and we put it into a container, it's going to basically fill both the volume of the container as well as take on the shape of that container. So if we look at this diagram right over here, you notice that the gas has expanded to fill the entire container, so it's gone all the way up to the very top of the volumetric flask. And also, obviously, the shape of that gas is now being dictated by the container itself. Okay? Gases are the most compressible state of matter. So what do we mean by compression? Basically, what happens is that if we apply an exterior force, the gas particles that are, basically floating around will start to come into closer proximity to one another. So basically, if you have kind of a generic, bunch of gas particles floating around, if we apply some pressure, right, to the sample, okay, the gas particles will get closer to one another and subsequently take up less space. Also, gases will mix evenly and completely when confined to the same container, and we should be all very thankful for this characteristic because it allows us to have basically consistent mixtures of important gases in our environment. So obviously we know that air is a mixture of nitrogen and oxygen and various other gases, but the fact that all of those gases mix evenly allows basically us to breathe the correct amount of oxygen in different parts of the room, or also makes it where you don't have a buildup of oxygen in one area, and let's say there was an open flame, you could have a big old flare up in terms of a fire that was going on. So basically, the evenly and completely process, or the mixing evenly and completely, allows for some very nice features to be taken on. And last but not least, gases have much lower density than liquids and solids. We know that the spacing of gases, in terms of the particle spacing, is much larger than with liquids and solids, right? So that's one of the defining characteristics. So basically the same, the mass value that you would expect to have for a specific substance, if it's a gas, it's going to have more volume. And if you look at your density equals mass over volume equation, the more volume, you have a larger denominator. A larger denominator is going to give you a smaller density because it's going to basically give you a smaller number when you divide it into the mass. Okay, so these are the physical characteristics of gases. Please be familiar with them and basically understand how the gases behave when put in containers and things of that sort, because these characteristics are going to be key to you explaining if calculations that you've done make sense, and basically if showing that you actually understand what's going on, not just mathematically, but physically. So I think most of us understand pressure intuitively. Basically, it's a force applied over a specific area. So when you compare, let's say, the wearing of high heels to the wearing of flip-flops, okay, your feet are going to hurt a whole lot more if you're wearing high heels versus if you're wearing those flip-flops, because the force that your body applies basically to the shoe surface, or to the bottom of the shoe surface, is consistent. However, the area, when you compare the heel to the flip-flop, obviously changes. So the area of the heel is going to be smaller, giving you a smaller denominator and subsequently giving you higher pressure when you divide that value into the force. Okay, so pressure is something that we pay attention to with respect to our gases, okay, how much pressure that gas is exhibiting on a surface, is something we pay, close attention to. So the Pascal is a unit, okay, of pressure, and 1 Pascal is equal to 1 Newton per meter squared. Okay, so remember, pressure is force over area, so the Newton is a unit of force. Okay, the meter squared is obviously a unit associated with area. Okay, so this is the SI unit for pressure. However, there is a slew of other pressure values that you will see and need to be able to utilize in order to do interconversions. So if you look at this basically chain of equalities, okay, this chain of equalities tells you the equivalency of each of these units to another unit. So what do I mean by that? Okay, so what this is telling you is that 1 ATM is going to be equal to 760 millimeters of mercury. 1 ATM is also equal to 101.325 kilopascals. Okay, 1 ATM is also equal to 760 torr. 1 ATM is equal to 101.325 bar. Okay, we can also interrelate any of the others, any of these other units to one another. So it doesn't just have to be through the 1 ATM. There are 101.325 kilopascal in 760 torr. Okay, there's 760 torr in 760 millimeters of mercury. Okay, so the interrelationships can all be met or understood by this basically equality set. So you want to memorize this set. This is what's going to allow you to do the interconversions. I will not be giving it to you on the exams or quizzes, so take some time to get used to these. So on a sort of interesting note, or you may not think so, but I do. So the unit of millimeters of mercury is actually related to the actual height of a mercury column. Okay, so basically what we establish as 1 atmosphere, or the pressure exerted by the atmosphere above us, is measured via a piece of equipment called a barometer. And basically what happens is that we have a pool of mercury. As you know, it's a liquid metal. Okay, and we have basically this eudiometer. Basically, it's a piece of glassware. It's kind of like a big narrow test tube. And we fill that up with mercury. Okay, we invert this tube into the pool of mercury that you see down here. And what happens is as the atmospheric pressure changes, okay, basically the height of your column is altered. So the more pressure we have from the atmosphere, the taller the column. So at what we call 1 ATM or 1 atmosphere, okay, we get a specific height of this mercury column. So 760 millimeters of mercury is what we measure here when we have 1 atmosphere of pressure pressing down on it. So 1 ATM of pressure is going to give us 760 millimeters of mercury in terms of the height of our column. Okay, so obviously this is related to an actual physical observation of a height. Now these other values, we've been able to do calculations and do different types of measurements to establish their relationships, but hopefully this will allow you guys to easily remember the 1 ATM and 760 millimeters of mercury relationship. So let's go ahead and apply this work that we just talked about. So in this case, we're being asked to convert the following pressures. Now, you're not always going to be told, hey, you need to convert this. When we talk about problems in the future, you're going to need to just know that the conversions need to occur based on unit evaluations and based on your understanding of how to properly calculate. But obviously, before you can do the more complicated equations and calculations, we need to be able to do these interconversions simply and quickly. So let's go ahead and look at that. Okay, just like with any other conversion, you're going to be utilizing basically your dimensional analysis setup. Okay, so what we are given is 22 millimeters of mercury. Okay, so 22 millimeters of mercury, Hg. Okay, that goes into that first box. Now, the question is, what do I want to convert into? Well, in this case, I want to convert into torr. Okay, so I'm going from millimeters of mercury to torr. So I need to look at the equality set up here, and I need to figure out what the relationship between millimeters of mercury and torr actually is. So if I find millimeters of mercury, 760 millimeters of mercury is equal to 760 torr. Okay, so that's the relationship, that's the conversion factor. Okay, so in this case, we're going to put what we want over what we have. So we want to be in torr. So I have 760 torr to 760 millimeters of mercury. Right? Okay, now obviously this relationship, the 760 and the 760 is a 1-to-1 relationship, so you're going to get the same numbers out mathematically. Okay, but your conversion process needs to be shown in this type of dimensional analysis approach. Okay, so millimeters of mercury are going to cancel out, so I'm going to end up with 22 torr as my new unit set. Okay, so pretty straightforward. So let's do another example set. Okay, so once again, I've been given 10 ATM. Okay, so 10 ATM is what I'm starting with. Okay, what I'm wanting to convert into is the kilopascal. Okay, now also guys, please notice that this is kilopascal, kPa. So the K is representing the prefix kilo. So just like kilometer or millimeter or centimeter or those types of things, this kilo is that same type of measurement. So if I were to be asking you to convert between kilopascals and pascals, basically that's just decimal movement. The Kevin hates dates because dates cost money approach, or you can use the relationship between, kilo and the base unit, just like you have in the past. So please understand that kPa, that K is a kilo prefix, so that if you need to make any other conversions, you can do so. Okay, now, so we don't care about pascals for this question, though. They're giving us kPa. That's what they want us to convert into. So if I come up here and look at my equality setup, I have 101.325 kilopascals for every 1 ATM. So that's my relationship. So I want to get into kilopascals. Okay. And 1 ATM is the relationship between kilopascal, 101.325 kilopascals and 1 ATMs. It's what I want on top over what I already have, which is ATM. It's going to allow my units to cancel out. ATM and ATM is going to cancel, and this is going to give me 1013.25 kilopascals as my pressure unit. So we can go ahead and look at the next couple calculations. So basically, I'm sorry, this should be 300 with a decimal. Apologize. Okay, so I have 300 torr, and I want to convert this into ATM. If I look at the relationship between torr and ATM, I see that I have 760 torr for every 1 ATM. Okay, divide those out, and that's going to give you 0.3947. Okay, so 0.395 ATM are the units you end up with because torr and torr cancel, ATM are left over. Okay, and last but not least, let's go ahead and go between torr and bar. Okay, so if I want to convert between torr and bar, 1.01325 bar for every 760 torr. That's the relationship. We're going to multiply this 2 by the 1.01325 and then divide by 760, and that's going to give us our units for bar, in our pressure in terms of bar, which is 2.66 times 10 to the negative third bar. Okay, so this is how you do your pressure conversions. Make sure that you're showing your work. If you're converting in between any types of units, you should always be showing how you're doing that, especially for pressure, since it's not just a decimal movement, it's actually a relationship between two different pressure values. You want to make sure that you're indicating that work. That work will be necessary for full credit on all of your work, so just make sure that you get used to showing it, and showing it in the format that we just discussed here. Okay, so now that we understand pressure, let's go ahead and let's look at a few things or a few details. So the force of the atmosphere or atmospheric pressure is basically equal to all of the weight of the air above you. Okay, so as we basically get closer and closer to the surface of the Earth, obviously we're going to have more and more atmosphere above us. Okay, so basically, if you live close to sea level, you're going to have basically all of that atmosphere above you. Okay, so you're going to have one atmosphere of pressure pressing down on you. If you climb higher, if you go, mountain climbing or whatever, the higher you get, right, the less atmosphere that is above you pressing down. So your atmospheric pressure as you go higher and higher in elevation is going to get less and less. And this causes different types of characteristics and features in terms of behaviors of gases, right? Different pressures are going to affect gases. And we'll look at those details and those types of questions a little later. Now, we've discussed this, but we're going to look at the measurement of atmospheric pressure. So we've already discussed this a little bit, but we'll go back over it one more time. Okay, so basically the atmosphere, or that all the air that is above you, is going to exhibit a pressure on you. Okay, and that's, as we said, the atmospheric pressure. Now, the value of your atmospheric pressure obviously depends on your elevation. The closer you are to sea level, right, the more atmosphere you have above you. Okay, so when you're at sea level, okay, the atmospheric pressure is going to basically be 1 atm. You have one atmosphere. You have all of the air that can possibly be above you. Okay, and so as we said, a barometer is that piece of equipment. You invert this tube of mercury into a pool of mercury. Okay, and basically the height of this column is going to be directly related to the pressure that the atmosphere exerts onto that pool of mercury. Okay, so 1 atm equals 760 millimeters of mercury. Once again, this relationship comes up. All right, now obviously if I were to take this barometer and go up to the top of Everest, I wouldn't have 1 atmosphere of pressure pushing down. Okay, so the height of my column in my barometer would decrease. Okay, so another thing that we need to mention or pay attention to is the concept of standard temperature and pressure. Okay, so these are values that you're expected to understand and know. If you're told, hey, this reaction is occurring at STP, or standard temperature and pressure, you should know that standard pressure is 1 atm and standard temperature is 0 degrees C. Okay, so this is memorization stuff. You need to know what these mean, okay, and basically be able to plug the appropriate values in. So another piece of equipment to be familiar with are manometers. Basically, they allow us to measure gas pressures. Basically, you have this system where you have a gas contained, and once again, that column of mercury is present. In a closed manometer system, as we release the gas, basically the gas is going to expand to a certain point, right? Okay, and basically it's going to expand and press. Okay, and press against the mercury column that you see here. Okay, so the height of your column in a manometer is going to be equal to the pressure of your gas. Now this is true when the system is closed. Okay, so that means that there's a vacuum up here. It's kind of like how we inverted that tube into the barometer's pool of mercury. Okay, you can also have open system manometers, and basically in this case, the gas is pressing against both the mercury as well as the atmospheric pressure. So in this type of situation, if you have an open system, you need to take into account the pressure of the atmosphere. So the pressure of your gas will equal the sum of the height that you now have plus the the atmospheric pressure that you see here. Okay, so in this case, obviously, if it was the exact same situation, exact same gas and volume and quantity of gas, you would obviously expect the height to be a tiny bit smaller on the one where the atmospheric pressure is also contributing to the force that's being applied to that gas. So we were discussing earlier the features, or the feature of compressibility that's associated with gases. Okay, and basically the apparatus that we have set up here allow us to kind of look at that relationship between pressure and volume. So basically what we're saying is that each one of these values or quantities of mercury is expressing or representing different atmospheric pressure totals. So in this case, this example, this quantity of mercury is showing 1 atm of pressure, 1 atmosphere of pressure. This example here is showing 2 atms of pressure, okay, atmospheric pressure, and this example here is showing 3 atm of atmospheric pressure. Okay, so basically we're doubling and then tripling the atmospheric pressure that's being applied to this volume of gas. Okay, so at 1 atmosphere, okay, you have 100 milliliters of gas. That's the volume of your gas. Okay, doubling the atmospheric pressure halves your volume of your gas, right? Okay, so if we now go over to tripling our atmospheric pressure, we've basically decreased our volume by a third. Okay, so what you should glean from this is that as pressure increases, your volume is going to decrease. So as I said, compressibility of the gas is a physical property that we need to understand, and hopefully you see this relationship very, very clearly from this diagram.